In this video, I'm going to show ABIT running inside QEMU with 254 cores. I'll also go through the kernel screens as well. We'll just reset the operating system. Here it's just going through preparing the memory, and what that does is just zero all the memory. There's 6 gig on the QEMU, and there we go. We'll go through the summary, the kernel summary. We're using PML for paging, that's all that's supported on this laptop, which will give us 256 terabytes of data. Available to every app is 39 terabytes. If we're using the PML5, it would be 128 petabytes of data. Everything on the screen we can see here. The kernel page size is 1 gigabyte. The server memory is 6 gigabytes plus the little bit required, which is basically a gigabyte for the QEMU, which we can see the memory used by BIOS. We can see the memory used by the kernel. The used memory and available memories down there, we've used a very small amount of memory. We'll have a look at the next screen, which is the Ethernet. We've got one network interface card here, and as you can see it's an Intel 82504EM, and we have all the information about this Ethernet card here. Now it's all set up and all the data that's coming through. The transmit buffer, the receive buffers, etc., which you can see here. The TX and RX. The next screen is all the PCI. We've got 2 NVM controllers, you can see at the bottom. Just above that is the Ethernet controller, and then we've got the other PCI devices in there. And again, we can go through and see exactly what's happening here. Depending on the PCI device and its functionality, we get more information. For example, this one here has MSIX, which we've set up. Very good. Very useful for debugging and running the system. The next one is the CPUs. We have 254. We can see the load, the interrupts per second. This is on the whole system. How many context switches, how many system calls, there's 2 per second. At the moment there's a user space application running, and every second it just updates a counter. And I'll show you that shortly. The system knows it doesn't need to do a context switch because it's already set up a memory on that CPU. So it just reruns the user space application every second. So we can go through and have a look at all the CPUs. We have a nice table here so we can go through and look at the performance and all the system metrics. There they are. Now we can go into every CPU and see what the CPU is doing. This tells us a little bit more information. This is for load balancing and stuff like that. So I won't go through them all, there's just a lot there. Now we can have a look at the NVMe devices. There's 2 devices and 2 controllers. And again, we can look at all the information for these. We have our system management BIOS, SM BIOS here. This just tells us everything about the system. And once again, we can go into the specifics of every single one of them, and it just tells us exactly what's happening. We have our interrupts, which is grouped into cores. So we can see what's happening on each core, what interrupts are firing. We have both the normal interrupts from the 808 6 days, and we have the MSI and MSIX interrupts. And as you can see here, for an NVMe controller, it's picked up MSIX, so it's using an MSIX interrupt. And there is that there. I'll just go back to the CPUs and we can see that we'll go to core 0. And you can see down here it's got attached MSI interrupts is 1 and just the normal interrupt system is 18, and they're in there. And now we'll go to the kernel messages, which is the boot up. I've disabled a lot of the boot up stuff. There's a lot of information that's duplicated, etc. that is not needed unless we have to debug something or find something out. It hasn't detected PML5, so we default into PML4. There's the compile date and compile time. It's the kernel C++ version is AVX, so it comes in 2 flavors, the kernel. It comes in SSE or AVX. If it detects AVX at boot up, it loads the AVX kernel, otherwise it defaults to SSE. And we support all of these extensions here, all the AVX and SSE and etc. The operating system is the shared user space. The entry point, that's for the developers. It's just a text screen. This is a cloud-based system. It doesn't need any graphics or USB or anything. It runs stuff in the back end. We support a maximum of 254 cores, and we support a maximum memory of 128 petabytes. The kernel segments just tell us about the kernel, where it's loaded, the read-only, the data, and the uninitialized data. Here's the E820 that we picked up from the BIOS. We've gone and added in the missing ones. And this is what we passed to the kernel. So we passed, this BIOS, this E820 to the kernel. We saw the memory preparing earlier, which just zeroes it. We put the memory into blocks, these blocks of 4096, 2 megabyte or 1 gigabyte. And this just matches the PML4 tables. So we can allocate memory in whichever block size we want, and that'll find it very quick. Bit of a hardware summary. PCI devices, the NIC devices, NVMe controllers, devices, and capacity. It started up the 253 AP cores and the BSP core. That's 254. Once all the cores have started, it releases the boot memory. And we set up the NVM controllers with completion queues and submission queues. We go through and create a root app base. So that is, any app base is, you can create multiple apps off an app base. So it's just like having a executable sitting inside a file system, and you can run it many times. So it sits there and it's all set up for performance to start up very quickly. And every app can have a list of libraries, and every app can also have a list of services. The root app base doesn't have a list of services, it just doesn't use any services, and it just uses the ABIT.core library. And then we go through and create the root application off the root app base, and with the section and stack code, the RO data, BSS and global is listed here to show us exactly what's happening in the memory side. And this is just for the root application. We then go through and list all the PCI interrupts. So whether these are MSI or MSIX, and then those get assigned to the CPU and everything else. Once the setup is finished or completed, we release the CPU boot stack. Every CPU has a stack upon booting. We then go through and create the assembly functions. So there's a lot of assembly code that gets automatically created depending on functionality required, what kind of cards are in there, whether it's interrupts or exceptions or Well, there's a bit of stuff that goes on there. And again, we just list out the PCI, the cores, NIC, the NVMEs, and the time it took to boot. The time it takes to boot is well under 1 second. That's about 0.1 of a second. But the time to boot with zeroing and preparing all the memory is about 15 seconds. So on this screen here, we can see all the kernel screens. If I take my finger off the control button, we now see the user space, and the user space has just got a log screen. And here we go. So every second we output to the screen hello from user space running, and we put in a little counter, and that's all it does there. So we can have a look at the CPU load, and CPU number 1 is the one that's running it. So there's 2 system calls there. One would be to display the text on the screen, and the second system call is to say I've finished running the routine. And that's it. I'll show you some more videos.